Welcome to Lesson 4 of Module 4 Ecosystem Dynamics. In this video, we're still looking at evidence for past changes. However, we are going to focus in this one on technology. And two of the examples we're going to look specifically at are radiometric dating as well as gas analysis. When we look at radioactive decay, there are two types of particles and one type of rays, which we can see. So alpha particles, they have a low penetrating power, but a high ionizing power. We have beta particles, and these are electrons from the nucleus when a neutron changes into a proton and an electron. They have a medium penetrating power and a medium ionizing power. And then gamma rays are photons of energy rather than a particle, and they have no mass or no charge. They have a low ionizing power but a high penetrating power. When we look at radiometric dating, we are using this technique to calculate the ages of rocks and minerals. And we do, in fact, use radioactive isotopes to do that. Over time, the isotope decays and energy and matter are released as radiation, causing the element to eventually become stable. This radioactive decay occurs at a regular measurable rate for each isotope, and it does form a stable daughter atom. This is known as the half-life, or the time taken for half of the parent atoms to decay. This is how, in fact, we are able to calculate the ages of rocks. When we look at carbon dating, this is the type of radiometric dating. It's used to identify the age of something that was once living. We can use carbon dating to extract information about the age of organisms within the fossil record. By measuring the amount of carbon-14 and carbon-12 in a dead organism, we are able to compare that with the amount in a living organism or the atmosphere, and it allows us to calculate how long ago the organism died. We can use carbon dating to estimate the age of organic matter that is between 5,730 and 50,000 years old. So here we have a few other isotopes that we may use to date and find out the age of an organism. And we can see here that we will use different isotopes depending on how old or young the fossil is, as each of these isotopes have a different number of half-lives, or a different length of their half-lives, however. So when we do want to measure this radioactive material, we can measure them using a combination of nuclear reactors, mass spectrometers, laser beams, and special microscopes. And in Australia, in 1908, I believe that's meant to say 1980, we saw the development of SHRIMP, which is sensitive high-resolution ion microprobe. And this allows us to date resilient grains of the mineral zircon. And it has allowed scientists to identify the oldest rocks on Earth. So just a reminder that that is 1980, not 1908. The mass spectrometers measure atoms and molecules that have been ionized. The chronometer monitors continuous streams of gas or liquid, and it allows us to give the age of meteorites. Survey meters are portable instruments that measure exposure to radiation. And cloud chambers detect radioactive decay with an ionizing particle forming a visible track in the chamber. Fission track dating, and this is where decaying uranium atoms leave marks in the surface of grains as they release particles and energy, and we can use electron microscopes to see these tracks. Their density is analysed and an age can be estimated. And then there's luminescence dating, where we measure the amount of radiation trapped in mineral crystals, and we do that using heat and laser light. The longer the crystal has been buried, the brighter the luminescence. And then we have gas analysis, and scientists can use the data in ice cores to reconstruct atmospheric concentrations of certain gases, particularly carbon dioxide and oxygen. And we can use these ancient carbon dioxide levels to infer past climates. Warming or cooling of the atmosphere would have had a direct effect on the types of plants and animals that are suited to survive in each climate. And we can see here that isotopes of oxygen give us a record of ancient water temperatures. And scientists can analyze these ratios in ice core samples and reconstruct water samples for ancient Earth. In terms of the technologies used for gas analysis, we have the infrared gas analyzers that measure trace gases using a beam of light and measuring changes caused by absorption. Optical sensors are used to determine the composition of C1 to C5 alkane gases. There's process gas chromatography that monitor continuous streams of gas or liquid for a range of process applications. There's laser absorption spectroscopy, and this uses the absorption of different wavelengths of light to identify the composition of a gas. And then there's photoionization detectors, which they expose the gas to photons of UV light, causing charged ion to form where the gas molecules absorb the high energy. That is lesson 4. Make sure you tune in for lesson 5.